Okay, thanks a lot. And thanks a lot for the invitation to this nice workshop. I'm happy to see that a lot of people are interested in developing homological methods for field theories. And my talk is about a similar subject, namely how to use homological algebra to understand a bit better how integrable field theories work in the well-known case of two dimensions and in also new and unexplored territories in higher dimensions. So this talk is based on joint work I've done together with my good friends Marco Benini and Benoit Vicedo in this paper. And in the second paper, this is about a higher dimensional case, also with our postdoc Ryan Cullinan. Okay, before I speak about the kind of results we obtained, let me first give you some motivation and background. Mostly, I want to explain what integrable field theory, according to my limited understanding of this subject, is about. So integrable field theories are typically appearing in two dimensions, in two space-time dimensions, sigma. By sigma, I denote a two-dimensional space-time. And the field theory on this sigma is usually called Lux integrable if the following is true. So you have the equations of motions of this field theory, and the equations of motions hold true if and only if a certain connection is flat. This connection is called the Lux connection, and it's a bit of a strange thing. It is a connection which is living on space-time, so it has a time and a space component, but it also depends meromorphically on some Riemann surface. So this connection, in order to make sense of this relation, equation of motion true if and only if the connection is flat, what you of course need is you need to express this connection in terms of the fields of the theory. Now, integrability can be phrased in this way in higher generality for generic Riemann surfaces, but in this talk I will mostly focus on CP1, the Riemann sphere. The papers we wrote have some details about the higher genus case in case you are interested in this topic. So why is that integrability property, why is that useful? Why is that a good thing to have? And it is useful because it has an important consequence, namely being able to rephrase the equations of motion in terms of flatness of a connection, depending meromorphically on some spectral parameters. You can now take the holonomy of this connection along Cauchy surfaces. Remember that we are living in two space-time dimensions here in this case. So the Cauchy surfaces are one-dimensional, so you can parallel transport along the Cauchy surfaces. What you get then is a holonomy depending on time. And it turns out that this holonomy does not really depend on time exactly because the connection is flat. So the time derivative of this trace of the holonomy is zero. So what you get is a time-independent quantity, which however also depends meromorphically on the Riemann surface. So what you can now do is you can do a Laurent expansion on the surface and thereby get a tower of infinitely many conserved charges. Conserved in the sense that they are time independent, because this here holds true for the whole holonomy. So the key point about integrability, at least from my perspective, is that you can build these infinitely many conserved charges, and then people have developed over the years techniques which allow you to use these charges to exactly solve the field theory in the sense of writing down explicit solutions of the typically highly nonlinear equations. Now, this traditional point of view on integrability is, however, a bit strange because the way how it's phrased here is a bit strange. Yeah, you have to find a Lux connection built from the fields depending meromorphically on a Riemann surface, which at the level of the field theory wasn't even there. So here we don't even have Riemann surface. So you have to invent a Riemann surface. You have to invent a way how to build a connection from the fields in order to encode the equation of motion differently. So it's completely unclear from this perspective what is the origin of the Lux connection and how can I systematically find it in examples. So how people have dealt with this issue in the past is that in the earlier days of integrability, people have developed a good feeling, a good intuition for how this works, and based on educated guesswork, they could construct Lux connections in a quite huge class of examples. However, the actual origin, the conceptual origin, remained mysterious when using this educated guesswork approach. A more modern point of view, which I come back in the next slide, is that you can use gauge theoretic methods to explain the origin of the Lux connection. So Lux connection is in some sense related to a certain gauge field, and I will explain that in a moment a bit more. So the kind of approach I will take here is I will now review a bit about this modern gauge theoretic point of view towards integrability, and then rephrase that from my own point of view. Okay, so the notion of gauge theory, which is linked to integrability, is what people call a topological holomorphic Chern-Simons theory. I will say a few words about this here. So the main idea, which goes back to works of Costello and Yamasaki, is the following. And this idea, a posteriori, after they tell you that idea, of course, completely makes sense. But it is, in my opinion, a very excellent achievement of these two, that they were able to identify and phrase this idea. So the idea is as follows. Since Lux connections are very fundamental for integrability, because they provide the conserved charges, they provide the kind of tools in order to construct explicit solutions, one should try to develop a mother theory describing Lux connections, and then from this mother theory extract models of two-dimensional integrable field theory. So it's kind of turning around the traditional approach. Traditionally, you start from some PDE for your fields, and you try to construct the Lux connection. Costello, Yamasaki say, go the other way around. Develop a theory for Lux connections and extract from it integrable field theories. And this mother theory can be realized by a topological holomorphic Chern-Simons theory. The manifold this theory is defined on is the product manifold consisting of space-time and the Riemann surface. So this is also a posteriori clear because you want to have a Riemann surface, so you have to plug it in as the input of your theory, and the gauge theory is defined on both the Riemann surface and space-time. Now, the action of this gauge theory, of this topological holomorphic Chern-Simons theory, is a bit strange. We have seen that already in the previous talk, but it looks roughly like that, or it looks exactly like that. So this action is defined on a certain type of gauge fields. These are not ordinary gauge fields on sigma times c, but these are gauge fields which are modeled on the de Rham algebra on sigma. So these are de Rham differential forms. However, on the Riemann surface, you just take Dolbeault forms. So these are the gauge fields here. They are kind of a mix of some topological gauge fields, so modeled on the de Rham calculus, and some holomorphic gauge fields, which are built on this Dolbeault complex. Now, with these types of gauge fields, you can build a Chern-Simons-like term. So you have the differential. The differential here is the de Rham differential on sigma, the Dolbeault differential on C. You have the usual Lie bracket because these gauge fields are valued in a Lie algebra. And this is some invariant pairing on the Lie algebra. Now, what this kind of expression produces uses free form, which you cannot integrate over this four-dimensional manifold. So what you need is some other datum to write down an action, and this other datum is a choice, a fixed choice of a meromorphic one form on C. So then you can see when you count now the legs, you can build a top form from this expression, and so you get some action when you do that. However, this action, as we have also seen in the previous talk, is a bit subtle and a bit it has some subtlety because omega, being a meromorphic one form, can have poles and also can have zeros. At the points of C where omega has poles, nothing guarantees that this integral can be performed, because omega diverges, so you don't know if the integrand is in fact integrable. So in order to get a well-defined action, you have to impose suitable, I will come back to that in a moment, boundary conditions on the field A. These boundary conditions at the poles of omega must be such that the divergences here compensate the zeros here, which the boundary condition enforces. However, omega can also have zeros, which means that the action becomes degenerate at these points. So you have to allow for suitable singularities in A at the points where omega has zeros in order to compensate that. Yeah, so you kind of have to do something to the gauge fields in order to, you have to define appropriately the space of gauge fields, not in this naive way, I will come back to that in a moment, in order to make sense of this action. Now, how the usual approach then works is, okay, so you impose some boundary conditions, you allow for some singularities, and then you perform some integrating out construction, which according to different people means different things, in order to reduce the theory from the four-dimensional manifold sigma times C to spacetime. So you integrate out the data on the Riemann surface. And this act of integrating out produces you a two-dimensional field theory on sigma, which turns out to be integrable because people can write down Lux connections, which also come from this higher dimensional point of view. So the goal of my talk is to give a mathematical description of this story. And this mathematical description I will phrase in the language of L-infinity algebras and homotopy theory, because this is a very suitable language to address exactly conceptual questions like what is going on here. Also, once formalized in an appropriate way, there's nothing special about two dimensions here. Instead of a two-dimensional space-time sigma, one can take a space-time of an arbitrary dimension and thereby make some statements about how integrability is supposed to work in higher dimensions. I will tell you more about that at the very end of this talk. Okay, a quick recap. I think everybody already talked a lot about L-infinity algebras in field theory, so I can be relatively quick and just say a few words from my own perspective. So L-infinity algebras are, by definition, graded vector spaces with a bunch of brackets on them, satisfying a bunch of identities. So L-infinity algebras are described by a lot of data, a lot of vector spaces, and a lot of maps between them. Now, what they do in physics is they give you a very efficient and powerful way to package exactly the required data to describe a classical field theory. In this picture, the L-infinity algebra encodes exactly information about the fields. This is in the degree 1 component of the graded vector space. The ghosts and higher ghosts, they're in degree 0 and lower, and the Andy fields, which are in degree 2 and higher. So this L-infinity algebra, the graded vector space of the L-infinity algebra, encodes precisely what are the fields, ghosts, Andy fields. Now, the brackets you have on this L-infinity algebra, they encode various things, and in particular, they encode information about the equation of motion, which in this language is the Maurer-Cattan equation for this L-infinity algebra. So you take an element of degree 1, apply brackets to it, put some 1 over n factorial, and sum it up, and then this is the equation of motion for the field theory described by this L-infinity algebra. You can also write down gauge transformations. These are infinitesimal ones, but the speaker before me also said a few words about finite gauge transformations. You can also produce formulas for that out of the brackets. And the gauge transformation parameters live in L0. The fields live in L1. And the way how the gauge transformations act on the fields is here encoded by another bracket expression of this type. And there are also formulas you can find for higher gauge transformations and various other things. So L-infinity algebras really package all the kind of data and structure you have to know about the classical field theory. All okay. There's one additional datum, which is very beneficial to have. And this is from the traditional point of view, an action functional. Yeah, because not every field theory, not every classical field theory must come from an action functional, but of course we like most those field theories which do. And an action functional in this algebraic picture of L-infinity algebras consists of a certain bracket, it's called a cyclic structure, of a certain degree, namely degree -3 in my conventions, which allows you to pair two among pairs of elements in the L-infinity algebra and produce numbers out of that. Now, from this cyclic structure, you can build an action. And when you vary this action, you indeed see that its equation of motion are the Maurer-Cartan equations. Okay, to give some easy examples. So the simplest example of a field theory is always a scalar field. A scalar field, you would usually write down an action like that, which I write in terms of the Rahm differential and the Hodge operator. So we have a kinetic term and some interaction term. Lambda n is the coupling constant for the phi to the power n plus 1 term. So it's a bit of a strange convention, but it becomes clear in a moment why. So if you want to encode this scalar field theory with a general potential in terms of an L-infinity algebra, it looks like that. So the underlying graded vector space has in degree 1 the zero forms. This is where the fields live. In degree 2, this is where the antifields live, the top degree forms. And the differential is what you get from the kinetic term, d star d. Now, the L-infinity brackets, the higher brackets for this, are controlled by these interactions. So we have the coupling constant, Ln is lambda n, the coupling constant, and then the Hodge dual of the product of fields. So the Ln brackets here are just they're not exactly the interaction potentials, but the derivatives of the interaction potentials. Now, the cyclic structure here is just integrating functions against top forms. Okay, now another easy example of an L-infinity algebra is the one for Chern-Simon theory. So in this case, you have the de Rham complex valued in a Lie algebra G. The differential is the de Rham differential, and the brackets which you need, because here the action is just cubic in A, you just have an L2 bracket, and the L2 bracket is just given by the Lie bracket on the de Rham, on the G-valued de Rham forms. And the cyclic structure is the invariant pairing and integration over M. Okay, so there are systematic ways how to translate traditional data like action functionals into L-infinity algebras and vice versa. This is the main point I wanted to do here. Let me now say a few words about the L-infinity algebra of topological holomorphic Chern-Simon theory. So this topological holomorphic Chern-Simon theory of Costello and Yamasaki, let's recall that this is defined on a product manifold consisting of a two-dimensional space-time sigma and the Riemann surface C, CP1 in this talk. You can describe this theory in terms of an L-infinity algebra. So the underlying graded vector space, or the underlying complex in this case, is given by the Rham forms on sigma, Dolbeau forms on the Riemann surface, tensor product of those. This hat here means a completed tensor product because these are Frechet spaces, so you have to use the right tensor product to produce the right type of forms. And this G here is a choice of Lie algebra, modeling the structure group of the Chern-Simon theory. So on this graded vector space, you have the brackets given by the sum of the differentials. So here you have a differential here, the Rham differential, and here Dolbeau differential. L1 is the sum of these differentials. And the L2 bracket is just given by the Lie bracket on G. Now, this is indeed describing the kind of features which Costello and Yamasaki wanted to describe, namely the Maurer-Cartan elements in this L-infinity algebra. They display the desired topological holomorphic behavior of this theory. So Maurer-Cartan elements, sorry, are elements of degree 1 in here in my conventions. Yeah, there are two ways how you can get an element of degree 1. It's a one form along sigma, which I write as A without calligraphic. Or you can have also 0, 1 form along C, which is this other guy, this theta. So there are two different parts of a Maurer-Cartan element here. One form along sigma and a one form along C. And the Maurer-Cartan equation, based on this L-infinity algebra for these elements, reads as follows. So the one form A along sigma is flat along sigma. Okay. That is kind of the feature one would like to have for a Lux connection. And the del bar of this one form is not 0. So this is not holomorphic, but it is something which depends on this other component, the form component along the Riemann surface. So in particular, if you would, so the traditional approach to how people would deal with this is they would gauge away this theta and then in this sense obtain something holomorphic. This is not what I'm doing here, but I just want to say that if you would be able to gauge away the theta, this goes away. You have del bar A equals 0, so you have a holomorphic connection depending flat, being flat along sigma. So in this way, you would find exactly the Lux connections you're interested in. How I would like to analyze this L-infinity algebra, describing topological holomorphic transdimensional theory, is a bit different, using techniques from homotopy theory, because this is the way how I usually think about problems. So in order to better understand what this theory here, described by this L-infinity algebra here, describes, let's integrate out the fields on the Riemann surface and see what it describes from the perspective of space-time sigma, where things are easier to interpret. Okay, so what does it mean to integrate out fields on the Riemann surface? So from this homological point of view, integrating out means that you have to compute cohomology, not the cohomology of the full complex. You just want to integrate out the fields on the Riemann surface. So what kind of cohomology you have to compute is that of the Dolbeault complex. Now, the cohomology of the Dolbeault complex, I write as H bullet here. You can link that cohomology of the Dolbeault complex to the Dolbeault complex itself with a strong deformation retract. So you can always find, for example, Hodge theory on the Riemann surface gives you that, a strong deformation retract which allows you to include the cohomology into the Dolbeault forms, project Dolbeault forms on cohomology, and here is a homotopy which describes that projecting and including is not necessarily the identity, but just homotopic to the identity. So these deformation tracts, which you, for example, get from Hodge theory, you can use in order to replace here the Dolbeault forms with the Dolbeault cohomology. Now, there is a bit of a detail I want to say here, a few words about. So here, this is just one of the components of this complex. Yeah. So you see that the field complex here has a bigrading. You have a grading of the form along the form degree along sigma, and the grading by the form degree along C. So these deformation retracts I'm speaking about here, they give deformation retracts on this bicomplex. But deformation retracts on bicomplexes you can always totalize to a deformation retract along the totalization. So you get a deformation retract for the L-infinity algebra by using a kind of quite easy totalization construction and these Dolbeault deformation retracts here. So if you do that now, you can show that this L-infinity algebra up here, based on the Ram and Dolbeault forms and this bracket, is weakly equivalent to a quite easy L-infinity algebra, namely the L-infinity algebra of forms on space-time with values in G, the Lie algebra, and just the de Rham differential and the bracket. So this L-infinity algebra here describes flat connections on space-time, flat connections without meromorphic dependence on the surface. The reason is, of course, that if you take CP1, here we make statements about CP1, Dolbeault cohomology of CP1 is just one-dimensional in degree 0 and 0 otherwise. So there's no you see nothing about the Riemann surface upon integration. Now that is of course a bit strange, yeah. So because the theory I've written down here, which looked like Costello-Yamasaki's topological holomorphic Chern-Simons theory, turned out to be quite trivial. So where is the integrable field theory and the Lux connection? Here, clearly not. Flat connections on sigma is something topological. It's a topological field theory. So there is no interesting integrable field theory or no interesting Lux connection at this point. So the reason, the kind of thing which happens here is that this theory, which I was introducing above here, is not yet appropriately defined, because from the traditional point of view of writing down an action, where was it? I said before that it's very important to allow the gauge fields to have some singularities at the zeros of omega, and also to have boundary conditions at the poles of omega. So these singularities and boundary conditions of the gauge field is very, very important to make sense of a theory like that. And these singularities and boundary conditions we have not encoded here. Yeah, so these are the Ram forms on sigma, Dolbeau forms on C. No singularities, no boundary conditions at this point. So in the way how singularities and boundary conditions can be nicely introduced in order to make this theory non-trivial is by using a few techniques from complex geometry, namely techniques of divisors and their associated holomorphic line bundles. So I say a few non-technical words about divisors. So when you want to describe poles and zeros of a meromorphic function, say, or meromorphic forms on a Riemann surface, you need some kind of gadget in order to kind of encode the location of the poles and zeros. So you have to say, here is a pole and here is a zero. And you also have to record the order of the poles and zeros. So these are the key invariants, the key information in poles and zeros of a meromorphic function. Now, these locations and the orders are naturally described by what is called a divisor. Yeah? So a divisor is a function with finite support from the Riemann surface into the integers. So what this function does is, to a point in the Riemann surface, it tells you what is the order of the zero or the pole of something at this point. Yeah? So you encode points and where something non-trivial happens. In particular, this meromorphic one form, which gives you an input date, which is an input datum for topological holomorphic Chern-Simons theory, defines a divisor. And this divisor encodes the locations of its zeros. So this I write as omega zero. This is the positive part of the divisor. Zeros are counted positively in divisors. And it also encodes the locations of its poles, which is the negative part of the divisor. Okay, so this additional datum Costello and Yamasaki use, this meromorphic one form, gives rise to a divisor which splits into two parts, zeros and poles. Okay, now what you can do with a divisor is you can assign to every divisor a holomorphic line bundle. I write that as LD. And this holomorphic line bundle has the following feature. When you take holomorphic sections of this holomorphic line bundle, the space of holomorphic sections is isomorphic to the space of meromorphic functions conditioned by the divisor D, which you use to build the line bundle. So this condition means that you have meromorphic functions whose poles and zeros are bounded by minus D. So for example, if the divisor is positive at some point, minus D is negative, and then this condition here tells you that F at these points is allowed to have poles of a certain order up to what minus D is. So this is the mechanism here. So you can take a divisor, so you can specify which kind of poles and singularities you would like to have, build a line bundle such that the holomorphic sections of this line bundle are exactly divisor condition functions. Now, the key feature of these line bundles or of these devices is that you can use the line bundles to twist the Dolbeault homologies, the Dolbeault complexes. And these twisted Dolbeault complexes, so these are Dolbeault forms on CP1 with values in these line bundles. And you see now that the homologies sensitively depend on details of the divisor, in particular on the degree of the divisor. The degree of the divisor is the sum over all its values. So it kind of tells you number of zeros minus number of poles weighted by multiplicity. So you see that the Dolbeault homologies change drastically on the divisor. In particular, you see that for positive divisors, you tend to develop zeros, Dolbeault homology, and for negative divisors, you tend to develop first Dolbeault homology. Okay, so you can play a game to modify the Dolbeault homologies by appropriately twisting with divisors. And that is precisely where the non-trivial features of integrable field theories and Lux connections in the Costello-Yamasaki theory come from. It comes from the fact that imposing boundary conditions allowing for singularities corresponds mathematically to twisting these complexes with line bundles coming from divisors. Let me say a few words about how this works. So the first thing I want to discuss is singularity structures. So singularity structures, I mean that structures which allow the gauge fields to develop singularities. So this is something which happens at the zeros of omega. The zeros of the meromorphic one-form omega, this is where A is allowed to become singular. And I'm now telling you a definition, or I'm proposing a definition of what I precisely mean by develop singular. Okay, so the definition goes as follows: a singularity structure for topological holomorphic Chern-Simons theory. So this L-infinity algebra we've seen before, built from de Rham-Dolbeault forms, is a decomposition of the divisor encoding the zeros of omega into two parts, d plus, d minus. And these two parts also have to be non-negative divisors. So this means the following: you look at all the zeros of omega, you look at where they sit, you look at their multiplicities, and you package them in two groups. You split them in two groups, d plus, d minus. Now, if you choose such a singularity structure, a splitting of this type, then you can play the following game. You can change the L-infinity algebra by twisting it appropriately with the line bundles corresponding to these divisors. So in order to do that, one has to be a bit careful, because when allowing for singularities, of course, performing brackets or applying differentials will generate more singularities. So you have to be very careful in order to distribute the singularities in this complex such that the L-infinity structure is still well defined on it. And the way, or at least the most general way I see how this goes, is the following. So you take the one forms along sigma, so these are the one forms along space-time, and you split them into their self-dual and anti-self-dual parts. This you can do because I assumed that space-time was endowed with an orientation and a metric, so I can have a Hodge star and I can split one forms into self-dual, anti-self-dual parts. Now, when I do this split, you see that here there are all these form components along sigma. This is the first index here. 0 forms along sigma, plus, minus forms along sigma, 2 forms along sigma. All these are one-dimensional as forms. I mean, there's one 0 form on sigma, one plus form, one minus form, and one 2 form on the two-dimensional sigma. So one meaning in a counting a basis. So so you see that here I decompose the fields in a way that I separate all the different form components along space-time. Now, after this decomposition, I can start twisting. I use the d plus divisor to twist the plus forms, the d minus divisor to twist the minus forms. And I also have to twist the two forms. How do I have to do that? Okay, I mean, here that divisor must contain singularities of both this and this. Why? Yeah, because you take a plus form and a minus form, you apply the bracket, you produce a two form. So the singularities here add up. So this is why this part here of the complex has to be twisted with the divisor of all zeros of omega. Now, the gauge transformation part, this is degree -1 in my, degree 0 in my convention. The gauge transformation part here, I cannot twist. Why is that like that? Okay, because zero forms, when you apply the bracket between zero forms and zero forms, you produce a zero form again. So whatever you would add here as a line bundle to twist, performing brackets will give you more singularities and more and more and more. So here that has to be without twisting. So long story short, using a singularity structure, you can build this new complex where different components are twisted by different holomorphic line bundles. Now, the result you can prove is that this L-infinity algebra of singular fields, you can realize that in a weakly equivalent way. You can again use homotopy transfer to twisted Dolbeault homologies in order to realize this weakly equivalent model. And this weakly equivalent model is given as follows. Here we computed the del bar, the Dolbeault homologies on C. So you see that here new features appear, meromorphic functions on C. They of course come by computing the Dolbeault homologies and using the main feature of divisors, that holomorphic sections of the line bundle are the divisor conditioned meromorphic functions. Okay. So here a meromorphic dependence emerges of the gauge fields. And here also meromorphic dependence emerges. So what you see now is that after twisting this topological holomorphic Chern-Simons theory with a singularity structure, with divisors coming from a singularity structure, you get a weakly equivalent description which looks exactly like the thing you want to have for a Lux connection. The connection, there's a plus-minus component of a Lux connection. They depend in some way meromorphically with controlled singularities on the Riemann surface, and they are flat. Yeah, because here it's the Raman differential in brackets, or the Maurer-Cattan equation for this L-infinity algebra. It's just flatness along sigma. So yeah, this notion of singularity structure thereby identifies what one means by Lux connections in this context. Now let's talk about integrable field theories and how they emerge from boundary conditions. So boundary conditions are something which you impose upon the already singular fields. So I'm now defining what I mean by a boundary condition B for the D singular fields we discussed on the previous slide. And what a boundary condition does is it's a family of non-positive divisors, B0, B plus, B minus, B2. So this 0 corresponds to 0 forms along sigma, plus minus to the chiral components, and 2 to the 2 forms along sigma. These divisors must be ordered in this way. This is again needed in order for the L-infinity structures to be well defined and what I'm going to define. And they have to satisfy a bunch of conditions. Condition 1 is that when you add B0 and B2, you get the whole divisor controlling the poles of omega. And the same happens when you add B plus and B minus. So in this sense, these B plus, B minus, B0, B2 are kind of partitions of the divisor, of the full divisor of omega into two parts. So this condition here is at the end needed to get a cyclic structure. I will say a few words about that in a moment. Then you have another condition which requires that the degree of the sum of the singularity structure and boundary condition divisors for the plus and the minus must be something very specific, genus -1 or -1, because we are here on CP1. So this is a bit harder to interpret, but the idea is the following. I say that in a moment when I'm writing the complex. Okay, so I come back to that. So a boundary condition, I mean this. Four divisors with this ordering satisfying these two conditions. Now, what you can now do with these divisors is you can twist further the, the complex underlying your L infinity algebra in the following way. You use B0 to twist the gauge transformations. So this imposes boundary conditions on the gauge transformations. You can use B plus, B minus to twist the plus minus components of the connection. And you can use B2 to twist this part. Now, thanks to these properties here, thanks to this definition, it turns out that this is an L infinity algebra because the differentials and the brackets are well defined on these divisor twisted Dolbeau complexes. Okay, now, so what happens now? Here I wanted to say something. Now here, we can try to see what these conditions here actually are supposed to do. Okay, so this condition here is just making sure that these Dirac differentials here are well defined. Yeah, because when you would have more boundary conditions in the forms, then here nobody ensures you that applying to a gauge transformation, the differential satisfies the required boundary conditions, which means that gauge transformations need more boundary conditions or equal boundary conditions to the fields. Okay, so this condition here is just to have the differential well defined on here. This condition here is required for having a cyclic structure. You see, when you now, a cyclic structure would pair this guy and this guy, for example. Now, when you pair these two, you get the divisor D plus D minus plus B plus B minus. Yeah. So the sum of all of them. And the sum of all of them is exactly the divisor of omega. So when you take the thing you get by pairing these two, wedge it with your omega, you get something without divisor. So something you can integrate. So this condition here ensures that you can define a cyclic structure on that. This condition here is the most tricky one, but it's also the most important one. You see, you want the degree of this divisor you use for twisting the one form parts. You want this degree to be -1, something very special. -1 implies that the Dolbeau cohomology, the twisted Dolbeau cohomologies here are trivial. So this is kind of important to get an integrable field theory. Why is that? So the integrable field theory should describe scalar fields, which kind of come from here. So the contributions to the fields when you pass here to cohomology, you want to go away. So this is what this enforces. You can also read it in a different way. You can read it in a way that it balances the singularities and boundary conditions for the gauge field in such a way that there are sufficiently many boundary conditions to fix uniquely the degrees of freedom you get from the singularities. You can also interpret that a bit more loosely. Now, long story short, you can run homotopy transfer to transfer this L infinity algebra down to the twisted Dolbeau cohomologies. And what you get now here is something which is very structurally very different to what happened before. The complex becomes shorter, so it just lives in degree 1 and 2. In degree 1, we have zero forms on spacetimes valued in some power of the Lie algebra, g to the power n. This n is some number which is related to the degrees of the boundary condition. Here you have two forms on sigma with values in the same g to the n, and the differential here. Now there happens something. You see that this differential is not linear in the Dirac differential. You see that it comes from the datum of the deformation tract, inclusion, homotopies, and projection, and to Dirac differential on sigma. So relative to sigma, this is a second order differential operator. So this complex here, or this L infinity algebra here, which is weakly equivalent to the one of Chern-Simon theories, boundary conditions and singularities, has exactly the kind of features of a scalar field theory. There are no gauge symmetries and a quadratic equation of motion. And these Ln brackets, you cannot make them, you can, if you work hard enough, make them explicit, but they are, for the moment, just determined by homotopy transfer. So you have a combinatorial way to compute them. So, okay, so my claim is that this weakly equivalent model for the boundary conditioned and singular fields, this model here is an integrable field theory. This is my claim. What can I, yeah?
Could you explain the meaning of G powered by n? What is Gn? Gn.
Which is what?
Yeah, Gn.
G to the power n, these are n copies of G.
Copies means that
It's not a degree, it's n copies of G.
The direct sum.
G plus G plus G.
Yeah. Thank you very much.
Okay. Now, as usual, you produce something by homotopy transfer, so you know a lot of abstract things. You know that it's equivalent to the thing you started from, and you know that there are formulas in principle for brackets. But one wants to understand a bit more what one can say about this field theory. So let me say, without doing any calculations or without doing much calculations, what one can say about this two-dimensional field theory I just produced. So here is again the underlying complex. So as I said before, the underlying complex resembles clearly that of a G to the power n valued scalar field. And the equation of motion, the linear part of the equation of motion, is a second order differential operator. Yeah. So this you see here, that is some kind of new feature which happens after you twist by boundary conditions and singularities. Now, if you look under the hood of homotopy transfer, so you kind of recall how these transferred brackets are constructed from certain trees, you can argue or you can show that the transferred brackets on this guy here contain exactly two sigma derivatives. Yeah. Like here, there are two sigma derivatives in the kinetic term. There are exactly two sigma derivatives splitted across all the legs in these Ln brackets. You can show that there's a degree -3 cyclic structure on here. This I already mentioned before. The singularities and boundary conditions are exactly balancing each other in a way that this thing becomes well-defined and non-degenerate. And this cyclic structure transfers to the two-dimensional field theory. So whatever two-dimensional field theory that is, it has an action function. And these are at least from my point of view, the characteristic features of a sigma model on sigma, which is valued in a Lie group to the power n, in n copies of a Lie group. So here, of course, an infinity algebras by construction just capture the formal geometry of a field theory, so the perturbative aspects of the field theory. So when you discuss a sigma model perturbatively, a G to the n valued sigma model becomes exactly, the fields are zero forms with values in the Lie algebra to the power n. Okay, so you see that these are exactly the features you want for a sigma model, a second order equation of motion, all the interactions also with two derivatives. There is an action functional, looks exactly, there are no gauge symmetries because there's no zero component in this L infinity algebra. So this looks clearly like sigma model. Now, with some computational efforts, which Benoit pushed ahead quite nicely, you can compute all the brackets and all the thing in easy examples. So take some simple example of meromorphic one form, then you can really compute not only the differential, but all the brackets. And you see that what this L infinity algebra describes is exactly a sigma model. So these homotopical techniques we developed reproduce at the level of these examples the expectations from the physics literature. Okay, now the most important question, in my opinion, is why am I calling this field theory I'm discussing before Lux integrable? I was always saying this is an integrable field theory and it looks like this and that. So what kind of structure makes this field theory integrable? And this is, from my point of view, the key advantage of this more abstract approach towards Chern-Simons integrable field theory business we are proposing, that it gives a precise notion in which this field theory described by this L-infinity algebra I produced before is Lux integrable. So the key insight or the key observation is the following. So when you have an ordered pair of devices, when you pass to the holomorphic line bundles, every ordered pair of devices you have canonically defined holomorphic line bundle morphism. So this is very crucial for what we are doing. Namely, we had not only one, but we had two L-infinity algebras, the one with singularity structures and boundary conditions, and the one only with singularity structures. Now, boundary conditions are non-positive devices, so they're always smaller than zero. So you can map from the L-infinity algebra with singularities and boundary conditions into the L-infinity algebra with only singularities, but forget the boundary conditions. Yeah, this is using these holomorphic line bundle maps. Now, when you combine that with the insights we've developed before, you see something quite cool. Namely, the L-infinity algebra describing a field theory, which looks like a sigma model on sigma, was weakly equivalent by construction, because we produced it from the homotopy transfer, to this L-infinity algebra of singular and boundary conditioned Chern-Simons fields. This maps, because of this map I explained here, to the L-infinity algebra of just singular gauge fields, which is equivalent, as we've seen before, to an L-infinity algebra describing Lux connections. So what you can now do is you compose all these maps. Yeah? So you go from the L-infinity algebra describing your field theory on sigma to here, to here, to here. So you get a morphism from an infinity morphism. So this is not a strict morphism. This is an infinity one because you did too much inverting quasi-isos here. So this is a complicated map, but again, you can compute it in examples. From which assigns to fields their Lux connections. So this kind of structure, that you do not have only one L-infinity algebra, but two, and the map between them, this kind of structure is what, in my opinion, describes integrability. That you have an assignment from your L-infinity algebra of field theory to an L-infinity algebra of Lux connections. And this assignment here comes out for free from our machine because of these maps you get for ordered pairs of devices. So you can say that this result makes precise the slogan which one often hears, that topological holomorphic Chern-Simon theory gives rise to both integrable field theories and their Lux connection. So these topological holomorphic Chern-Simon theories know about field theories and their Lux connections, and how they do is, yeah, you have these different divisor conditionings here. Okay, I am almost running out of time, so let me say in very brief words what happens in higher dimensions. Here I don't go into much details, I just want to sketch very briefly what changes and what doesn't change. Of course, from the mathematical point of view, not much changes once you understand the mechanism in a form I presented before in this talk. It's kind of obvious what to do in order to push to higher dimensions. Let me say a few details. So higher dimensions, I mean, there are various ways how you can go higher dimensions. You can replace the two-dimensional spacetime by a higher dimensional spacetime, D plus one-dimensional manifold. Or you can also push the Riemann surface into something higher complex dimensional. So the higher dimensions, I mean, here is higher spacetime dimension. So what was the two-dimensional spacetime sigma before will be now replaced by a D plus one-dimensional manifold, M. So D corresponds to the spatial dimensions. Um, how this works is as follows. So when you fix your number of spatial dimensions, then d plus 1 are spacetime dimensions, and you want to have a topological holomorphic Chern-Simons theory on m times sigma. So this is a d plus 3-dimensional one. So sanity check, the ordinary case, 2 dimension is 1 plus 1. So this is 4 dimensions. Yeah. So in general dimension, you can define a d plus 3-dimensional topological holomorphic Chern-Simons theory, but the datum you need for defining that is not an ordinary Lie algebra, but an L-infinity algebra. So controlling the gauge symmetry. So the gauge symmetries of this theory are not ordinary gauge symmetries, but higher ones controlled by an L-infinity algebra, D-term L-infinity algebra. So there's an L0, L minus 1, L d terms in total. So we end up at L 1 minus d, something like that. Okay, you know what I mean. When you write it out, this L infinity algebra is concentrated in 0 and negative degrees such that d terms are non-zero. So this d here, the categorical depth of the L infinity algebra, is linked to the dimension and is also linked to the dimension you want to have an integrable field theory on. So all these numbers d are linked here. In order to define this d plus 3-dimensional topological holomorphic Chern-Simons theory, you need this d-term L-infinity algebra and a cyclic structure. And this cyclic structure also has a non-trivial degree d minus 1. So in the traditional case, that's just a normal Lie algebra with an ordinary invariant pairing. But here in general dimensions, you need different algebraic inputs. Now, when you run the same games, you introduce a definition of singularity structures. You can extract from this L-infinity algebra one which describes higher Lux connections. And these higher Lux connections are indeed higher connections here because the structure, the algebra, is a higher Lie algebra. So these are higher connections. And they produce conserved charges living not only on one-dimensional cycles, but on k cycles of any dimension up to d. Again, the d appears here. Sanity check, d equal 1. So this would be along one cycles, but already for 3-dimensional integrable field theories, you would have also something living on 2 cycles. You can also you can write down a general definition of boundary conditions and then twist with these boundary conditions, and you see that you then get integrable field theories on the d plus 1-dimensional manifold M. And these integrable field theories you construct from this machinery are higher gauge theories. Their gauge symmetries go to degree d minus 1. So producing the integrable field theory decreases the depth of gauge symmetries by 1. That also was similar in the traditional case where we had a gauge theory and produced the sigma model as an integrable field theory. Here it's the same. But the key new feature is that these higher dimensional integrable field theories are gauge theories. Already when you go to 3 dimensions, these are gauge theories, and in 4 dimensions, these are even 2 gauge theories. And they are built from k-form fields for k running from 0 to d minus 1. And there's a certain pattern in which these tower of k-form fields interact with each other. There's a second order differential operator on the k form, first order differential operator on the k plus 1 form, a zeroth order differential operator on the k plus 2 form, plus nonlinear interactions you get from homotopy transfer is equal to 0. So the equations of motion of these types of higher dimensional integrable field theories are equations of motion for form fields of this type. An open problem, so you can say these things. I mean, the abstract machinery allows you to construct and prove some abstract nonsense about that. You can also prove that there is a map from the L-infinity algebra of the IFT to the Lux connections, and then you have a parallel transport for these higher Lux connections, etc., etc. So you can prove a lot of abstract things, but an open problem in this area is that I would like to see some non-trivial examples of higher dimensional integrable field theories and understand if and how they relate to models which people have studied in physics. So since I'm running out of time, I do that very, very quickly, this part. So we did a few calculations on a simple example, which already displays some, in my opinion, interesting features of integrability in 3 dimensions. So let me very briefly say that. So when you apply the general machinery to M, the 3-dimensional Minkowski spacetime, you see and simple choices. So simple choices, I mean that the structure L infinity algebra is just the shifted tangent L infinity algebra of an ordinary one. So this means that you have h in degree 0, h in degree -1, no differential, and the bracket as usual on that. So this is a very simple example of an L infinity algebra. And simple examples of singularities and boundary conditions you can compute explicitly the underlying complex of the 3-dimensional integrable field theory. So this looks a bit wild, but I interpret that in a moment. So you have here 2 rows. Here are the fields. So this 3-dimensional integrable field theory has a scalar field and a one-form field. The scalar field has some equation of motion with some constraints. It's already a bit unusual. And the one-form field has 2 copies of gauge transformations and the 3-form equation. So this is roughly what you see here from this complex. Here, the explicit formulas. You also see that the feature that second-order differential operators pop up is here again. So in these differentials, you see that they are second-order, del 1, del 2, along the coordinates pop up. Here, these Q1, Q2, Q3, they are the locations of the zeros of omega. So you take a simple choice of omega, which has 3 zeros, and Q1, Q2, Q3 are the zeros. Okay, now this looks pretty random. You can stare a bit at this equation, at these differentials, and try to interpret what's happening here. But what this describes is a scalar field, a one-form field satisfying some equations, having some gauge symmetry, and you can analyze that now. What is, in my opinion, quite interesting is that in this construction, I just took R3 with a choice of coordinates. I didn't equip that with a metric. I chose a frame on R3. And what happens is quite interesting here, namely these locations of the zeros of omega, Q1, Q2, Q3, they make a notion of geometry emerge in the integrable field theory. So details of the one form on the Riemann surface encodes geometry on spacetime in the following sense. This L infinity algebra here admits Green's operators. Green's operators in the sense of, in a homological algebra sense, which I don't want to explain now in detail because it would take me too long. But this L infinity algebra admits Green's, or this complex admits Green's operators. And these Green's operators are linked to those of the Laplacian for this metric. So even though this looks pretty wild and there's no D'Alembert operator in this complex here, there is an underlying D'Alembert operator which controls the solution theory of that guy. And this underlying D'Alembert operator is obtained from a metric, and this metric is obtained from the positions of the zeros of omega on CP1. And this is quite nice. I mean, this in particular tells you that there's a well-posed initial value problem here because you have Green's operators, which you can use to solve that. So this admitting Green's operators or homological notions of Green's operators is here already quite nice, and that they're linked to a Lorentzian metric is also quite nice. Now, when you study this model in a bit more detail, you see that it shows a bunch of similarities to another known 3-dimensional integrable field theory in a different kind of approach, namely Ward's 3-dimensional integrable field theory. And these similarities, I cannot comment now very detailed on them, so Benoit understands that way better than I, but one can say a few things about the similarities. But what is still missing is a detailed comparison or a detailed analysis of this model, also including the interactions, so including the L infinity structure and how it relates to other things people know. Okay, that's my talk. Thanks a lot for listening.
Very much. So from on-site, is there any question or comment?
Can you perform the quantization in the sense of similarly to Costello and William textbook?
Yeah, the quantization here, good question. So this is something we will be looking at. So you have all the, so what do you want to quantize? You want to quantize probably these wait a second. I lost my slides. Anyhow, so here there are a lot of L infinity algebras in the game. So the one which admits a quantization is this one here, because this has a cyclic structure which is intact. This one doesn't have a cyclic structure. So you can ask about quantizing the theory on sigma times C, or quantizing directly the integrable field theory. So these are two things you can ask. These are equivalent descriptions. So the challenges in quantizing will be equivalent. There's one thing which prevents you from running the usual factorization algebra machinery, namely that these complexes here are not necessarily elliptic complexes. So this you see here, these complexes, even in this example, in the three-dimensional example, this is a hyperbolic complex. It's not an elliptic one because it admits Green's operators corresponding to a wave operator, to an hyperbolic partial differential operator. So this is not an elliptic complex, so you cannot use elliptic regularity and the usual renormalization machinery to run quantizations for that. You would need something more adapted to Lorentzian signature. And so there are some techniques which were kind of originating from algebraic quantum field theory, which might be more useful for that. But the standard Costello-Quilliam machinery does not universally apply because we are not sure. We can get here elliptic complexes and hyperbolic complexes and everything in between. So it is model dependent. Does that answer your question?
Yeah, thank you.
Any question?
So in two-dimensional case, if we have a flat connection, we
Mhm.
get conserved charge, but in higher dimension, now we have a molecular element of general Olympic algebra. Then how to get a conserved charge?
Okay. So these okay, I would like to write. The Lux connections here in higher dimensions, they are also flat connections, but flat higher connections. So one has to be careful here. So the datum replacing the ordinary Lie algebra is a D-term L infinity algebra. So this is an L infinity algebra concentrated in degree 0, -1, -2, up to until you hit D terms. Now, when you take the tensor product of this guy with the Ram forms on M, you see that you have multiple ways of getting a degree 1 element. You can have a 1 form on M valued in the 0 component of G, a 2 form on M valued in the -1 component of G, etc., etc. So here, this notion of Lux connection is a higher connection, meaning that it's a 1 form component, 2 form component, etc., etc. Satisfying a flatness condition. Yeah, flatness condition is the Maurer-Cattan equation for the Ram complex on M times G. Yeah. So these higher connections, they have parallel transport, not along one-dimensional lines only, but also along two-dimensional surfaces, three-dimensional cubes, or depending on how high your connection is. This is what I meant by saying it here. So there are parallel transport constructions which allow you to take flat connections valued in a higher Lie algebra and produce parallel transport along cycles. So these you can algebraically describe in the paper we wrote. We gave a link. There's, what's this guy's name? Abad something. I forgot the guy's name. So there's a nice homotopy algebraic description of these parallel transport constructions, or there are also geometric descriptions going back to Schreiber and Waldorf and friends. So yes, there are parallel transports, but they are along higher dimensional surfaces as well. And this is where the conserved charges live. So here the conserved charges come in different types. They live in codimension 1, so on Cauchy surfaces. Then there are other conserved charges living in codimension 2, 3, all the way down.
Thank you.
Yeah. So I presume not all integrable models can be realized that way. Is that correct?
I don't. It's a good question, and I wouldn't know how to mathematically phrase that. What one means by all integrable models. So
Just like Toda models, or some maybe some models could not be realized that way. I'm not sure. It's a question.
I don't know much about this example business here, but I know from what Benoit told me that people were able to produce a huge amount of known integrable models from this Chern-Simons theory, and also found a lot of new ones. So I'm not sure if there is one example of an integrable field theory which people were not yet able to design in this language.
Nope.
So I think it's pretty universal, but it's an open problem if it really captures all integrable field theories, whatever that means. But it is known to capture a lot of them.
So the question then I have is, could you, a posteriori, could you perhaps see the L infinity structure being related to this Lax pair directly, like the horizontal arrow, without going through this embedding in this top, or is that
this one?
Yeah.
So the horizontal arrow, okay, this one here, directly without going through. I think this was the traditional approach. So when you have here, this is literally in examples a sigma model, yeah, an integrable sigma model written in L infinity algebra language. And this weakly arrow was typically the guesswork, because what you have to do is you have to minimum you have to map between Maura-Cartan elements, yeah. So you have to assign to every solution of the equation a flat holomorphically dependent connection. So if you don't go through that machine of 4D of higher dimensional Chern-Simons, you would have to guess how this map works. And then I think one is back at the traditional approach to integrability, where you have a field theory, you know what you mean by Lax connection, and you try to guess a map, how to assign to fields Lax connections. The advantage of this gauge theoretic approach is that there's no guess. It's basic homotopy theory and this observation that different divisor conditionings have different features.
Yeah. And another thing, so if you're at the bottom left corner, instead of integrating out on the Riemann surface, could you also integrate out on space-time and see what you get on the Riemann surface instead?
I didn't ask that question. Integrating out space-time, so yeah, good question. I don't know. What could that actually mean? No, I didn't think about that. I wouldn't know how to interpret that.
Yeah.
So integrating out space-time, I think people usually interpret that as some kind of scattering amplitudes, or is that right? Integrating out space-time would mean passing over to strict solutions and minimal model for scattering amplitudes or something. So yeah, I wouldn't know what to. Integrating out fully would give you the scattering amplitudes, right? But integrating out just that, interesting.
But just purely algebraically, you would probably also get some homotopy transfer to some cohomology now of the differential on space-time rather than
Yeah, that works the same way. So the key thing was that there is, you have always this bi-complex here. So what we did is we computed cohomology here from a deformation retract and kept the space-time forms intact. You can do the same here, and then there are concrete totalization constructions of deformation retracts. If you have a deformation retract from here down to the Rahm cohomology, you can integrate also that out and see what comes.
yeah, just curiosity. Thank you very much.
Any other question? No? Then how about online? From Zoom, is there any question or comment? No question. Yeah, then let us thank Alexander-san again.